Okay. So now we are going to discuss how we implement simple linear regression model using Python libraries. Okay. So, you can go with this file. I already executed everything and keep it aside for the workshop purpose. So just I am implementing everything in the Google Colab because I'm not using the machine learning model for a larger data. So that's the only demonstration purpose. This is sufficient. So as usual, so here my application is I want to predict the number of sales based on the cost of advertisement. Here, the application that what we are going to discuss as part of implementation of the simple linear regression model is estimation of number of sales based on the amount we spent on the advertisements. Okay, na? So as my data is available in the Google Drive, so again, so as my available in that Google Drive, so just already mounted. Okay, just mount your Google Drive. Again, I'm saying that mounting a Google Drive onto the Google Colab is not a mandatory. I am mounting the Google Drive every time because, sorry, I'm mounting the Google Drive everything because my data is stored in my Google Drive. My data is stored in my Google Drive. Connect to Google Drive.
Please share your screen.
Oh, thank you very much, sir. Okay, hope it is visible now. So just I'm mounting the Google Drive. This is mounting the Google Drive. Now, as usual, I am importing the required libraries like NumPy, Pandas, and Matplotlib, that is for the pictorial representation for the graphs drawing. So I'm trying to import this one also. Now, my project now is I want to estimate the sales of a company based on the advertisement cost. Based on the advertisement cost. Okay. And this whole data is already stored in my Google Drive. Already stored in my Google Drive with the name of sales data CSV. If you want, click this folder, go to Drive, and go to my Drive. Under AI data, you can see sales data CSV, this part. So this sales data CSV, simply you can see the 3 dots. Click here and copy path and paste here. Okay. Now I am using the pd.read CSV. Why CSV? Because it is the extension of CSV. I am reading the data from this path and store the data into the file with a variable name data. Just simply run this one. Okay. So whatever the data available in the CSV format is stored with a variable data as a data frame. This is the input advertisement. These are the sales or the output. I want to predict the sales based on the advertisement cost. This is the input and this is the output. This is the X and this is the Y. Now you have to separate X and Y. X is the advertisement, right? Input advertisement, nothing but X. Output Y, nothing but the sales. So Y equal to sales output. Y equal to under the data sales column. Under the data sales column, what are the values are there? All the values stored with variable Y. This is the output. Similarly, under the data frame with advertisement column name, what are the values are there? Those values are stored with a variable X. So X is the input and Y is the output. X is the advertisement, Y is the sales. Okay. So that's how I am separating the input and output. That's how I'm separating the input and output. Okay. And some things I want to skip, all the things not required. So now you have to convert into a single array. Single array means one column and multiple rows. One column, multiple rows. You have to reshape your input and output. You have to reshape your input and output. So -1, 1 means you are converting the X array with one column and multiple rows. That is based on the number of values are available. So once you have the X and Y values, so now we are going to split the data. Now we are going to split the data. So how we split the data? We can use the train underscore test underscore split that we discussed in the just now and yesterday also. So for the train underscore test underscore split, we have to pass your input X, output Y, test size. Nothing but the how much percent of data you want to use for the testing purpose. I am using the 0.33, nothing but 33% of data I want to use for the testing. So random state that equal to 42, 10, whatever you want, you can keep that value. So what this method will do, it will split the data into training input, testing input, training output, and corresponding testing output. Like that, it will be split. Up to here, same what we did for the previously for the simple integration model. Up to here, the same, no change. Loading the data and splitting the data. After that, now actually, if you want to train the simple integration model, if you want to train the simple linear regression model, so we have to initialize the M and C values. We have to write the two for loops, all the things we did in the previous session. Now I want to use the library. If you use the library, just these 3 lines are sufficient to train, to initialize and you train your simple linear regression model. To initialize and to train your simple linear regression model, these 3 lines are sufficient. But whereas in case of the previously what we did, so it's not right actually. No, it's not. So previously we initialize the M and C values, we initialize the eta value, we initialize the maximum number of iterations, and we wrote 2 for loops, outer for loop for the iterations, inner for loop for the samples. And inside the 2 for loops, we are keeping the gradient calculation, we are calculating the step length, we are updating the model parameter. All these codes are we have written if you want to train the simple integration model. But if you want to use the libraries, then just 3 lines of code is sufficient to initialize and you train your simple linear regression model. So if you want to take the simple linear regression model simply from sklearn, you get the linear model, sklearn.linear model, import linear regression. Import linear regression. Okay, from sklearn.linear model, import linear regression. Now create an object. I am creating an object with name LM. You can create an object of your choice. Whatever name you want to give, you can give that name here, not a problem. So LM equal to, just I am creating the linear regression object. Just I am creating the linear regression object. So once you create the linear regression model object, now to train that linear regression model, simply use lm.fit. lm.fit. So to train the machine learning model, which data is required? Training data is required, right? So that's why I am passing the X train and Y train. I am passing the X train, that is the input data in the training set, and Y output data in the testing set. You have to pass the X value and Y value in the training set to train the linear regression model, simple linear regression model. If you want to train the simple linear regression model, simply use lm.fit. That's it. lm.fit. So the training was completed. The training was completed. Now, I think if you are able to remember, after training, what we observe after training a simple linear regression model with the 2 for loops, with the gradient calculation, with the step length calculation, all the things, what we observed, what is the final M and C values? What are the final value of the M and what is the final value of the C? What are the final values of the model parameters M and C? So the training was completed, 3 lines. Now, if you want to print that M and C values, so if you want to print that M and C values, so if you want to know M value, M equal to LM, that is your simple linear regression model object, dot COEF underscore, that is the coefficient. So that will give your M value. Similarly, LM, that is the object of your machine learning model, dot intercept, that will give the C value. We know that in the Y equal to MX plus C, C is called as intercept. So that intercept will give the C value. Once you got the M and C value, simply print that M value and print that C value. That's it. If you run this code, you will get the what is the value of the m and what is the value of the c. M value equal to 0.93 and C value equal to 2.55. But if you want this M and C values, what we did earlier, we write around 10 to maybe around 10 lines of code. But here it's not required. Only if these 3 lines of code provide the M and C values. Okay, that is the use of Python libraries. You no need to write the code from the scratch if you want to implement any machine learning model. But if you are a research scholar, if you are a faculty, if you are a UG student, if you are a PG student, it's better to understand what happened behind every machine learning model. That is required. So that's it. Training was completed. And finally, I am getting the updated model parameters M and C. Okay. Now, I want to go for prediction. Training was completed. I want to go for prediction. So we predict the values based on the trained machine learning model. So what is the trained machine learning model? LM is your trained machine learning linear regression model, simple linear regression model, right? So if you want to predict something using that same trained linear regression model, then how will you do the prediction? LM dot predict. LM dot predict. I want to do the prediction with the training data. Similarly, I want to do the predictions on the testing data as well. So if you want to find the predictions based on the training input, and if you want to go for test outputs, predictions based on the testing input. So here I'm passing xtrain to get the predicted output on the training data, xtest to get the predicted output with the testing data. So just you have to run this one. So tell me what y underscore pred underscore train will have. It will have the predicted output by simple linear regression model for the given inputs coming from the training data. Y-pred test is nothing but have the predicted outputs by a simple linear regression model for the inputs coming from the test data. For the inputs coming from the test data. Okay, so this is what you have. I think you are clear, right? What mean by Y-pred train? What mean by Y-pred test? All the things. Okay, now I don't want to go for this pictorial representation. We don't have much time actually. But anyhow, I will share these all Colab notebooks I will share with you. You can practice. It's not a big deal. It's not a part of any machine learning, but just I'm trying to visualize how the outputs will be, how the predictions will be. Fine. So once you got the Y-pred train, that is the predictions by the simple negation model on the training data, prediction by the simple negation model on the testing data. And tell me which variable holds the actual outputs on the training and on the testing. Those are the Y-train and Y-test. So Y-train and Y-test are the actual outputs. Y-train and Y-test are the actual outputs. Whereas Y-pred train, Y-pred test are the predicted outputs. Now, if you want to observe the performance of a simple linear regression model, you have to measure the errors. The errors are based on the difference between your predicted output and actual output. Your predicted output on the actual output. Okay. So now we are going to discuss about the error matrix computation. Error matrix computation. Okay. Now, generally, it is a regression problem because we are trying to forecast or to predict the sales. Sales is any number. Sales may be a 10, sales may be a 20, sales may be a 30, sales may be 100, any number. So it is a regression problem. If it is a regression problem, how we evaluate the performance of a regression model? Based on the error matrix. What are the error matrix? You can consider mean absolute error, or you can consider mean square error, or you can consider the root mean square error. If these errors are very less value, then you go with, you can say that your model is performing well, then you go for the real-time deployment. So if you want to find the mean square error or mean absolute error, simply first you have to import the math library. Already imported, you no need to call again, but anyhow, keep it like that only. If you want the metrics, from sklearn.metrics, import mean squared error. From sklearn metrics means error metrics, import mean absolute error. Okay. So if you want to calculate the mean square error, so MSE mean square error equal to mean square error function you have to pass actual output and predicted output. Is the training performance. That's why I'm passing only training data. Actual training output, predicted training output with the training data. Similarly, if you want to calculate the mean absolute error, so call that function mean absolute error and pass the actual output and predicted output on the training data. So error is nothing but the difference between the actual and prediction, right? That's what I'm trying. Actual prediction. And RMSE is nothing but I will write, otherwise if you have any confusion. So MSE, mean square error, equal to mean square error. That means sigma I equal to 1 to n, total number of samples, actual value minus predicted value whole square divided by 1 by n. That's called as the mean square error. And mean absolute error is nothing but the 1 by n sigma I equal to 1 to n modulus absolute y minus yp. This is called as the mean absolute error. Where if you want to calculate the RMSE, root mean square error. So see this one, mean square error. How we calculate mean square error? 1 by n sigma equal to 1 to n y minus yp whole square, where y is called as the actual output, yp is called as the predicted output. On that we have the root. So this is how we can calculate the root mean square error. So these are the different error metrics can be used to evaluate the performance of a model. So to get this square root, I am importing the math library here. This is the math. So how we calculate the root mean square error? Root mean square equal to math.sqrt, square root. The square root of your mean square error. This is a mean square error that will give the root mean square values. And all the values are I am printing here. So this is the root mean square error, this is the mean square error, this is the mean absolute error. These all are the training errors. Okay. Later, if you want to find the same RMSE, mean square error, and mean absolute error for the testing data, simply pass actual test output, predicted test output, actual test output, predicted test output. Then you will get the testing errors. Okay. So you can write here this testing error. So generally, this training error or testing error are used to observe the performance of any machine learning model. Let's assume I'm happy and you are happy and your client also happy with these errors. Then what you will do? You are going to deploy the machine learning model under the backend of your application. Clearly observe here, please. Up to this part, it's okay. It's okay. Up to here, you train the model, you test the model, assume that your model is performing very well. Your model is performing very well. Your client also happy. But your client don't want this complete code. What he want an application. So if your application means you have to deploy this trained model. You have to deploy this trained model. So if you want to deploy the trained model, so first of all, what you have to do is you have to save your trained model first. Whatever the model is trained and tested, which is performing well, you have to save the model first. How we save the model? So you have in the .pkl form, we are saving the machine learning models. We will save the machine learning model in the .pkl format. Okay. So if you want to save the models, import pickle, import pickle. And I want to save my simple linear regression model with the name of model.pkl. You can give any name. You can give any name. If you want to save the simple linear regression model SLR, you can write SLR. So I want to save my trained and tested simple linear regression model with the name of slr.pkl. Your choice. Okay. Now, up to now, with which name your simple linear regression model is available? Up to now, with which name your simple linear regression model is available? With the name of LM. With the name of LM. So that's what I'm writing. You have to use that name now. So pickle.dump, you have to dump your trained model. You have to dump the trained model with the file. What file? slr.pkl. That means whatever the model, trained model is there, I want to store like slr.pkl. Okay. So whatever doing, maybe for this complete project, you may spend, for example, I'm saying for any machine learning project, you spend 2, 3, 4, 5 months of time. And finally, whatever you are doing, everything will be over. Finally, I want this model only for the application development. For the application development. So now I want to run this cell in order to save my machine learning model with a name of slr.pkl. So you can simply run. Done. You can observe here pkl file. You can see slr.pkl. So you can download this file, click here. You can download this file and deploy in your application wherever you are working. Not only on this machine, in any machine you can download it and send it to that machine and you can deploy the application there. Okay. But forget about all things what you did till now. You forget about all the things. Only this part is required for you in the deployment. So machine learning model deployment in the backend of an application is nothing but just keeping this file. Okay. So now I save the model. That's fine. Now I want to deploy the model in the application. I want to deploy the model in the application. Okay. Deploy the model in the application. So if you want to deploy the model in the application, this is the application part. If you want to deploy the model in the application, first of all, you need to load the model which you already saved on your computer. You have to load the model which you already stored in your computer. So model equal to pickle dot load. So you have to load the pickle model. What is the name of the model? Model dot pickle, right? No, because we stored with the SLR. So you have to write SLR. Okay, ne? So SLR pickle, you have to load it. And that load model is stored with the name of model. Now your application will ask the user to enter the advertisement cost. How much cost it is, you have to enter, it will ask. And if you whatever value you are passing through the input command will be stored in the form of the string. But your sales is not a string, it is a number, right? That's why I am converting into the float. I am converting into the float. So I am converting this user IP into the float and stored as a advertisement. And I am converting that advertisement as a array. At advertisement as a array, whatever the input, single input I am getting, I am converting as a array. Now that input, I am saying that advertisement cost is 25. If advertisement cost is 25, what will be the my prediction? Prediction means whatever the sales. So prediction equal to my load model dot predict, and you have to pass the number of sales, sorry, number of advertisement cost, total amount of advertisement cost, that is ADV. Once you pass this value, then your model will give the prediction value. That prediction value I am storing advertisement cost, this one, and my result, nothing but the prediction cost is this one. So just simply run this one. So now it is asking, what is the prediction advertisement cost? I am entering advertisement cost is a 30 lakhs, let us do. So it's saying that advertisement cost is 30 and the sales is around 30.62 something value. Okay. So this is how we are deploying your this part from here, this part and this part comes under the deployment of your model. And this is the back end of your front end, back end of your web page. Once you click on the submit button, your code should be like this. And finally, it will print the result value, prediction value on the another page or maybe displayed on the same page. So this is how we train, test, and load the machine learning model using the Python library. Here we discovered the only simple integration model. Okay, done. Now I want to stop this simple integration model. We discussed the mathematics behind the simple integration model. We implemented based on the mathematics what we discussed in the Python, and also we implemented using the Python libraries. That's over. Now we will move to the multiple linear regression model. Now we will move to the multiple linear regression model. Please listen carefully. Done. Fine. So now we will discuss about the multiple second one. So multiple linear regression model. As the name suggests, this multiple linear regression model is used for the regression problems. Regression problems. Okay. And this is the supervised learning model. Supervised learning model. That means if you want to train this model, you require both input and output. You require both input and output. So what is the difference from the simple regression model and the multiple linear regression model? In the simple regression model, the model will predict a output variable based on a single input. One input and one output in case of the simple linear regression model. Whereas in case of the multiple linear regression model, you have the multiple inputs. You have the multiple inputs. Let's assume I want to forecast the load at a particular time on a substation based on the load available 1 hour before, based on the load available at 2 hours before, and based on the load available at 3 hours before. That means there are 3 input features. So these are called as the input features. And this is your target variable or the output variable. So you are going to predict some output, you are going to predict some output variable based on the 3 input variables. Based on the 3 input variables. Based on the 3 input variables. Okay. So that means multivariable. That's why it's called as a multiple linear regression model. Whereas in case of simple regression model, we will use only one input and one output. Here we can use the any number of input to predict some output variable. Okay. So for ease of understanding, I don't want to take L of t minus 1 or L of t minus 2 or L of t minus 3 or L of t. And normal notation I want to consider as my inputs are x1 and x2 and x3 and my output is y. My output is y. Y is the actual output. My output is y. That is called as the actual output. Okay. Now, hope you are clear with this one. Now, how your multiple linear regression model will be? How your multiple linear regression model will be? We will discuss. So this is called as MLR, multiple linear regression model. Okay. So in the multiple linear regression model, it will accept any number of input features. It will accept any number of input features. So that means, so you have x1, you have another input x2, and you have another input x3. Okay. Now inside your multilinear regression model, you have the one model parameter that is called as M1, nothing but the coefficient of the first input feature. And you have the another input variable and another model parameter M2, that is the coefficient of the second input feature, and M3, that is the coefficient of the third input feature. Okay. And that means M1 into X1, M2 into X2, and M3 into X3. And we will add all the things. We have to add all these things. We have to add M1 into X1 plus, M2 into X2 plus, and M3 into X3. We have to add all the things. And we have one more summer circuit, that is the plus, and we have the bias parameter that is called as the CR intercept. And finally, you will get the output. Finally, you will get the output. This is your predicted output from your machine learning model, multiple linear machine learning model. That's how your multiple linear regression model looks inside. I said earlier, machine learning model, don't panic about that word. Machine learning model is nothing but some mathematical process, some mathematical operation inside it, but we don't know that one. It is like a black box. So I'm trying to open it. What is inside? What is inside? I'm trying to open it. Okay. So this is how your simple linear regression, multiple linear regression model looks like. So from here, the predicted output yp equal to m1 into x1 plus m2 into x2 plus m3 into x3 plus. See, this is what your output. And whatever the output is there, because it is a supervised learning, that output, let us assume this is the x1, this is the x2, this is the x3, and this is the y1. So for x1, x2, x3, the predicted output is m1 x1 plus m2 x2 plus m3 x3 plus c. That is the yp1, let's assume. So that is compared with your actual output. That is compared with your actual output, that is the y1. So whatever the difference between your predicted output and your actual output, based on the difference, based on that error, your model parameters will be updated. So what are the model parameters here? What are the model parameters here? Our model parameters are M1 and model parameter is M2 and model parameter is M3 and C is the another model parameter. Okay. So this is how your multiple linear regression model looks like. Now we will discuss how we update the model parameters using the gradient descent algorithm. What happened for a multiple linear regression model during the training process, that we will discuss now. So I think you are clear up to now. I'm asking the small question to all of you. If anyone able to respond, please respond. So you can respond through chat box also. Chat box also. My question is, let's assume I want to predict the load on a substation at a particular time based on last 3 hours load data. Last 3 hours load data means now time is 2:30. I want to predict the load at 3 o'clock today. Based on the load available at the 2 o'clock, 1 o'clock, and 12 o'clock. And also based on the load available yesterday, 3 o'clock, day before yesterday, 3 o'clock. So this is my process. That means last 3 days and last 2 days data. Now tell me, if you want to use the multiple linear regression model, how many model parameters will be exist in that multiple linear regression model? I think you are clear with my problem statement. I want to predict the load on substation at a particular time based on the last 3 hours load data and also based on the last 2 days load data. Last 2 days means if I want to predict the load today at 3 o'clock, so based on the load available at the last yesterday 3 o'clock and day before yesterday 3 o'clock. If that is the case, how many model parameters will be? I'm asking. So Vijay is responded, but once check Vijay. So not 5. You said it is a 5, not 5.
6, sir.
Yes, it is a 6. So we have the 5 inputs, right? 5 inputs means 1 hour before, 2 hours before, 3 hours before, 1 day before, 2 day before. Total 5 inputs, 5 coefficients. M1, M2, M3, M4, M5. In addition to that, you have the one bias parameter, that is 6. So total 6 model parameters. That thing we have to know. So if we concentrate on only libraries, we don't know what happened inside. If you understand open the machine learning model, then you can get every information. Fine. So that's it. This is the total number of model parameters are 6. Now we will discuss about how gradient descent algorithm will help to update the model parameters of your multiple linear regression model. Now we will discuss. Step by step process we will discuss now. Now tell me, in case of the machine learning, I said already, we know already, right? What is our error function? Error function equal to stochastic gradient. Error function equal to 1 by 2 yesterday. That means yesterday, no, day before yesterday we discussed it. 1 by 2 into actual value minus predicted value whole square. So that error function E equal to 1 by 2 into y minus m1 into x1 minus m2 into x2 minus m3 into x3 minus c whole square. This is my error. Out of this, what are the model parameters? Model parameters are, our decision variables of the model parameters are m1, m2, and m3. Whereas, sorry, c also. Whereas this y, x1, x2, and x3 are called as the data coming from your data set. So m1, m2, m3, c are the model parameters. Y, x1, x2, x3 are the from the data set you are getting x1, x2, x3, and y. Okay. Now, I think everyone following class, at least if you are unable to, at least you are releasing the everyday videos. So if that is the case, anyone can tell me, based on knowledge you gained with a simple linear regression model. So in case of multiple linear regression model, also same process. Anyone? So what will be the first step? Step 1. So what is the step 1 here? So step 1 is you have to read data. So your data contains x1, x2, x3 and y and number of epochs, maximum number of epochs and learning rate, eta, and you have to initialize model parameters. You have to initialize model parameter M1, M2, M3 and C. And also you have to read total number of samples in the training data set. You have to read total number of samples in the training data set. So I'm using the stochastic gradient. So anyone respond if you're able to. Step 2, what the step 2? So you have to set outer for loop, that is the iteration. So iter equal to 1. What is the step 3? That is the inner for loop. That is nothing but we are starting from the first sample in the data set. What is the step 4? At least this is very, very important. What is the step 4? Anyone, please? If you are unable to use the mic, just if possible, just text. Yes. So as your one of the participants told, we have to calculate the. We need to calculate the gradients. Not only GC, Vijay, we need to calculate the gradients with respect to the every model parameter. We need to calculate the gradient with respect to the every model parameter. That means you have to calculate the GM1, we have to calculate the GM2, we have to calculate the GM3, and also you have to calculate the GC. So anyone can tell me what will be the GM1 value. So GM1 value nothing but so G gradient equal to your error function with respect to your model parameter, right? So what is the GM1? So you have to differentiate error function with respect to the model parameter M1. Then what happened? These two come forward, 2 will be cancelled. So we have the y minus M1 x1 minus M2 x2 minus M3 x3 minus C. And we are differentiating with respect to the M1 gradient M1, right? So what is the M1 coefficient? Minus x1. So minus x1. Similarly, GM2 equal to y minus y M1 x1 minus M2 x2 minus M3 x3 minus C into x2. Because my M2 coefficient is minus x2, is minus is here and x2 is here. Here M3 coefficient is minus x3, so minus y minus M1 x1 minus M2 x2 minus M3 x3 minus C into x3. And what about the GC? GC means what the coefficient of C? Minus 1 only. So minus y minus M1 x1 minus M2 x2 minus M3 x2. So this is how we can calculate the gradients. That's it. So if the complexity of the model increases, definitely your number of gradients increases, number of computations increases. So complexity of the algorithm also increases. You require the more computation power. Okay. So what will be the next step? Step number 5. Anyone, please? Step number 5. What is the step number 5? What will be the step? Yes, delta. Very good. So you have to calculate the delta. Delta means change in step length. So that means you have to calculate the delta M1 and delta M2, and you have to calculate the delta M3. We have to calculate the delta C. We have to calculate the delta C. So that's equal to, so what is the delta M1? How we calculate the step length? Delta M equal to minus eta into gradient, right? So here also same. Delta M1 equal to minus eta multiplied by my gradient with respect to the M1, GM1, this value. That will be coming here. Okay. And similarly, delta M2 equal to minus eta multiplied by GM2 and minus eta multiplied by GM3 and minus eta multiplied by GC. That's how we can calculate the what's called step length. So after calculating the step length, what will be the next step? That is called step number 6. So what is the step number 6? So what will be the step number 6 after calculating the delta M1, delta M2, delta C? That's nothing but the step lengths. So next step will be updating your model parameter. How we update the model parameters? So delta C equal to M1 equal to M1, sorry, updating the model parameter M1 equal to M1 plus delta M1 and M2 equal to M2 plus delta M2 and M3 equal to M3 plus delta M3 and C equal to C plus delta C, where M1, M2, M3, C are initially coming from here. And those values will be updated based on the values what we are getting here, step lengths. So after that, you have to go for the step number 7. So step number 7 is nothing. So as I said earlier, step number 4, gradient calculations. Step number 5, step length calculation. And step number 6, update of the model parameters will be repeated for every iteration and every sample. Will be repeated for every iteration and for every sample. Okay. So now what will be the step number 7? Step number 7 means you have to update your sample number. Sample equal to sample plus 1. First it is sample equal to 1. First sample, with respect to the first sample, we update in the model parameter. Now we are going to the second sample. Next third sample, fourth sample. Now what will be the step number 8? So here what we are going to do is, if your current sample value is greater than n, that means n means number of samples in the training data, is greater than n. So there are the two possibilities, either it may be a true, it may be a false. If sample number is greater than n, that means your sample number exceeds the number of samples in the data. That means there is no samples are available to train, to use for the train. It is true. Then go for the next step. Suppose if the current sample number is not exceed the number of samples available in the training data, that means it's a false, then anyone respond to which step we have to move. To which step we have to move. If the number of samples is less than, the current sample number is less than the total number of samples available in the data, yes. Step number 2, you said no. No, Vijay, clearly observe. So as I said earlier also, same. Iteration 1 means first iteration, update the model parameter with respect to the sample 1, sample 2, sample 3, sample 4. If all the samples are completed, then only you have to go for the next iteration. So suppose if the sample number is less than or equal to n, that's greater than n is the false, means less than or equal to n. So still there is a few more samples are available to update your model parameters. Then to which step we have to move from here? So we have to go to the, again, we suppose initially step sample equal to 1, right? After implementing the step 4, step 5, step 6, now sample equal to 2. When sample equal to 2, again you go to step number 3, then again sample 1. Right? So it is wrong. So think properly, then you can respond to which step we have to move. See, let's assume I have the 4 samples. Initially, I am the first sample. Calculate the gradient, calculate the step length, update the model parameter. Now sample becomes 2. I have the 4 samples. Now we are moving to the second sample. Now if we are moving to the second sample, from there where we have to go? That's what I am asking. So we have to go to the step number 4 again. Again, with respect to the second sample, calculate the gradient, update the step, calculate the step length, update the model parameter, and go to the sample number 3, sample number 4. If all the samples are completed, then only go for the next iteration. So if it is a false, you have to go to the step number 4, go to gradient again. Next step means step number 9. So step number 9 means you have to update your outer for loop. That means iter equal to iter plus 1. Now step number 10. So what is the step number 10? You have to check whether your current iteration number is greater than the number of epochs that you initialize at the time of your initialization. If it is a true or false, we have to check. If it is a true, if it is a false. If it is a true, you have to go for the next step. If it is a false, then you have to go for the what step? Step number 3 now. You have to go to step number 3. Step number 3 See, one iteration is completed. In the next iteration, again start from sample 1. Sample 1, sample 2, sample 3, all the samples in the training data. For every iteration, you have to repeat that one. Okay. Suppose if all the epochs are completed, you are reaching the maximum number of epochs, then what you have to do? Simple. Step number 11, print or read model parameters, calculate errors on both training and testing, and deploy your model provided you and your client are happy with your errors. So this is the algorithm that is used to train the multiple linear regression model. For multiple linear regression model. I think you are clear with this complete algorithm. Okay. So if it is based on our case study, if it is a 5 input features, then definitely we have the GM1, GM2, GM3, GM4, GM5, and GC. 6. We have the 6 equations. Here also 6 equations. Here also 6 equations. So as the complexity of the model increases, definitely number of equations increases, number of lines of code increases, your computation increases, you require more computation period. And also you have required more memory to store all these model parameters. So that's why when compared to your machine learning, if you go for the deep learning, you require a more RAM and more processing speed, more RAM to store all the runtime variable created to store those values and also store your model. All things you require the more computation power and more RAM. Fine. I think you are clear with respect to your multiple linear regression model training algorithm. Here also I am using the gradient descent algorithm only. Maybe you will ask why when you are using the gradient descent algorithm, sir. This is the part gradient descent algorithm. Why you are using the gradients here? Based on the gradient descent algorithm suggesting. As per that only we are creating these gradients. So that's how gradient descent algorithm is useful in case of the machine learning. Done? Fine. Now it is the 220. Now we will discuss implementation. We will discuss about the implementation. So multiple integration model with the sample data. Later we will discuss about the libraries. See, okay, fine. I think most of things you already know. So this is the data. Dear parts, this is the data. X1 and X2 are the input features. Y is my output variable or the target variable. That means based on the values of X1 and X2, I want to predict the output Y. Based on the values of X1 and X2, I want to predict the output Y. So X1, X2 are called as the input values and Y is called as the output. Okay. Now, so as usual, because this complete data is stored in my Google Drive. So that's why we need to mount. We need to mount my Google Drive into the current Google Colab environment. To mount your Google Drive, you can keep this line, 2 lines of code, just to connect your Google Drive. If you observe here, nothing is available here. Once you run this cell, then you will find the Google Drive here. Once it is mounted, okay, mounted. Now, as usual, I think not much explanation not required here. You have to say now you can see the drive. In the drive, in my drive, in the Google Drive. In the AI data, I have the different data sets. Okay. Now run this cell to import all the required libraries. Now the data what you have seen here, that is available in my Google Drive with the name of sample data underscore 02 CSV. Right? So that path I have written here. What happened here? Whatever the data is available in this path, the data is read and stored with a variable called data. Now, if you run here, these are your data set. This is your data set. Okay. So I think only for the workshop purpose, for the demonstration purpose, for the easy of understanding the participant, I'm taking the very, very small data sets. So I don't want to go for again this step outliers. Already we discussed for the simple linear model. Same thing will be there only. And I know there are no outliers and there is no missing values because the data set is very small and the data set I have prepared. So I know everything is fine. That's why I'm not executing this cell outlier treatment and also missing value treatment. I'm skipping all these missing value treatment and also outlier treatment because I know there is no outliers and missing values. But I will share all these notebooks with you. You can practice for your project. You can change some modifications in the code and you can use it as it is. So now we are going to split the data. We are going to split the data. Okay. So if you want to split the data, we know that from sklearn dot model underscore selection import train underscore test underscore split. Okay. Now in data, we have all the inputs and outputs, right? Whatever the values are there, I want to store with the name of data frame. With the name of data frame. So all the values available in the data are stored here. Okay. Now, what are the x and what are the y? Y means that last column. So that's why I'm keeping the -1. So colon, comma, -1 means -1, -2, -3. In Python, this is the -1 index, -2 index, and -3 index. Okay. So -1 means y column. So that is the y. So these values are stored with a name y. And up to -1, that means up to this one, what are the values we have x1 and x2 are stored with y. Are stored with y. Okay. So that's how I am splitting the input and outputs. What are the inputs? X1 and X2 are the inputs, right? So this is X1 and X2, and this is the Y. And the Y is stored with Y, and where X1 and X2 are stored with capital X. So capital X holds all the input feature values. Small y holds the output variable values or target variable values. Now, train underscore test speed, you have to pass the input features, you have to pass the output feature, you have to mention the test size, how many number of samples you want to keep for the testing day. That is the 20% of data you want to keep for the testing. Now, run this cell, then I think you know about all the things, right? What it will do, it will split the whole data for the training and testing. So xtrain means input features for the training data. Xtest means input features x1, x2 for the test data. Ytrain means output values for the training data. And ytest is the output values for the testing data. Okay. So after data split, now tell me what is our first step. And now tell me, anyone, based on this problem, based on this project, how many number of model parameters will be? How many number of model parameters will be? So we discussed one problem right here. So based on this problem, how many number of model parameters will be in your multilinear regression model? How many number of model parameters will be in the multilinear regression model? Right. It is a 3. Model parameters are 3. One is the x1 coefficient, another is the x2 coefficient, another is the bias parameter C. So there are the 3 model parameters. So these 3 model parameters we are going to initialize, right? You can see our notebook. We have to initialize model parameters. Here 4 model parameters. Here we have only 3 model parameters in our program. So 3 model parameters we are going to initialize M1, M2, and C randomly initialized between -10 to +10. You can choose any range. I'm considering -10 to +10. In addition to that one, you have to initialize your learning rate and you have to initialize the maximum number of epochs or the maximum number of iterations. This is called initialization, first step, step 1. Now, code. But before going to the code, what we have to do, actually, we required gradients, right? gm1 equal to minus y minus m1, x1, m2, x2, m3, x3, see like that. So these gradients, I want to write a small function. I want to write a small function to calculate the gradients. Okay. So that function I want to show now. So gradient calculation, define function with the name gradient. So to calculate the gradient, what are the values are required? M1, M2, because we have the three model parameters, M1, M2, and C. So M1, M2 required and C required. M1, M2, and C. And also we required inputs, right? I think you are clear. Inputs also required, X1, X2, and Y also required. So X1, X2, and Y we had to pass. And now we know M1 derivative, that means GM1. M2 derivative, that is the GM2. C derivative, that is the GC. You can write, if you have any confusion, you can write GM1, that is the gradient with respect to the M1. GM2, gradient with respect to the M2. GC, gradient with respect to the C. Okay. And these three values we are going to return. So you have to give the gradient with respect to the M1, gradient with respect to the M2, gradient with respect to the C, we have to pass. Okay, just run this cell. That's how we can calculate the gradients. Now coming to the algorithm. So we know there are two for loops, outer for loop for the iterations, inner for loop for the number of samples. Number of samples nothing but the number of rows in a training data, this part. So outer for loop, inner for loop over. So inside the two for loops, what we have to write? First, we have to calculate the gradients. So to calculate the gradients, so this is the function I am using. I think you are clear with this one. So for the gradient calculation, what we require? M1 is required, M1, M2 required, M2, C required, C. Okay. And X1 is nothing but the in the training data first column. That's right. First column is X1. Python, first column nothing but the 0 index. Second column nothing but 1 index. That's why first column means it is the 0. Second column means this is the 1. Third only two columns, right? For inputs X1 and X2. And Y is the Y train. Output, right? Output where it is available under the Y train is available. Y it is a sample. Y I'm taking the sample. If sample equal to 1, so first row, first column, first row, second column. These are the X1, X2, and first value in the Y train. That is the output. Right? So this will give the values of GM1, GM2, and GC. So you can write otherwise, it will give the GM1, GM2, and GC. So once you calculate the gradients, GM1, GM2, and GC, now you can calculate the step length and you have to update the model parameter. In this code, I am updating the model parameter directly. Otherwise, you can write, after calculating the gradients, we have to calculate the delta M1. How we calculate the delta M1 equal to, not delta M1, change in delta M1 equal to minus eta multiplied by gradient GM1. I hope you understand. And delta M2 equal to, that means delta M2 equal to minus eta GM2. And and delta C equal to minus eta into GC. So this is the GM1, GM2, GC, delta M1, delta M2, delta C. Now M1 update, M2 update, M3 C update. M1 update nothing but M1 plus delta M1. M2 nothing but M2 plus delta M2. This is what we discussed already, this part. And C is nothing but C plus delta C. Right? So like this, your model parameters will be updated. Once the complete training process is completed, final M1, M2, C model parameters will be printed. That's it. So these are the final model parameters. M1 value is 2. M2 value is 3, approximately 3. And M4 value is 4. That are the values, right? Hope you understand. Nah? So After training was completed, what we have to do? We have to observe the performance of a model during the training phase. So performance of a model is nothing but the calculating the error metrics. If you want to calculate the error metrics, first of all, you have to predict the outputs. You have to find the predictions. You have to collect the predictions of your trained machine learning model based on the input data of a training. We have a training input and output, and give the input data, training input data to your model. Once you give the training input at your model, whatever the predictions are coming, that predictions you have to compare with your actual output, then you will get the errors. So if the errors are less, then your model is perfectly all right. If not, you have to think over what you have to do further. So first of all, if you want to calculate the errors, if you want to calculate the errors on the training data, you have to calculate the predictions on the training data. If you want to calculate the errors on the testing data, you have to calculate the predictions on the testing data. That's you have to remember. So my goal is I want to do the predictions on the training data and testing data. So this is the code I am writing. Okay, because I'm not using any libraries. That's why code is somewhat lengthy. Okay. So I am using one yPredTrain variable to store all training predictions. Initially it is null, later I will update. What I have to do, I have to take every sample from my data, every input from my training data. So every input contains x1, that is the 0th index first column, x2, that is the first index second column, and y, that is called output. We have the x1, x2 and y. You have x1, x2 and y. Okay. So those values I have to collect from the training data. And those values are falling to the m1 into x1 plus m2 into x2 plus c. That is the what prediction your machine learning model will give. So we discussed already. That's why I'm saying it open. m1 x1 plus m2 x2 plus c. That's what I'm writing here. m1 x1 plus m2 x2 plus c. That gives the prediction. And whatever the prediction is there is appended and stored in this variable. So finally, you have a matrix called y underscore pred underscore train, which has the prediction output on the training data. So just I'm running this complete cell. So you have the complete predictions here on the training data predictions, predicted output with the training data. Whereas the actual output is available in the y train. Similarly for the testing, same code, but this time, because I want to store the testing predictions in another variable, that's why I use the y underscore pred underscore test. And I have to take the every sample from the test input. And I have to take the test input x1, test input x2, and output from the y test. And m1 x1 plus m2 x2 plus c. That will give the prediction. That prediction is stored in this variable. I think it's clear. Right? So now, simply I want to tell y train contains the actual output. Y pred train contains the predicted output. Your machine learning model predictions with the training data. Y test contains the actual outputs in the testing data. Y pred test contains the predictions by your multiple linear regression model with the test inputs and the testing data predictions. So these are testing data prediction, testing data, training data prediction. This is the actual output in the training data. This is the actual output in the testing data. So once you have the predictions, now you can easily calculate the errors during the training and testing. So I discussed already here. Only thing is, if you want to calculate the training errors, you have to pass y train and y pred train. Actual output in the training and predicted output in the training. Now simply run this one. So my errors are almost zero. My errors are almost zero only. 10 to the power minus 21, 10 to the power minus 11, 10 to the power minus 11 is the zero only. So that's fine. That means there is no difference from the actual output and your predicted output. So my model is perfectly well in the training. And also I will see for the testing also. Now if I train this one, in the testing also I have the errors minus 10. That means 10 power minus 10, 0. 10 power minus 20, 0. 10 power minus 10, 0. So everything is fine. So I am very happy with my training performance and the testing purpose, because in the both cases all errors are zeros. So I am happy. So if you are happy with your performance of a model during the training and testing, and if your client also happy based on the training and testing performance of your machine learning model, now you are going for the deployment. Now you are going for the deployment. So deployment means what? Your front application will ask the inputs x1 and x2. Once you click on submit, backend application, you have to pass these x1, x2 values to your multilinear regression model based on the mathematical relation inside your multiple integration model, like m1 plus x1 plus m2 x2 plus c, it will give the predictions. That's what I am writing here. First, your application will ask the x1 and x2 values. It will ask x1 and x2 value. So I am printing the x1 and x2 values. Whatever the user is entering, that x1, x2 values are printing. Now, these values are going to the machine learning model. What is the mathematical relation for the machine learning model? M1, x1, M2, x2 plus c. I am using the float because whatever the values are entered from the front end, it will be taken as a string, but it is a number. That's why for the typecasting, I am using the float. I am converting the string into the float. Once you calculate this mathematical process, then you have to print that output value. That's the prediction. If I right click here, you can take any value. So let's assume I want to consider 0.1, 0.2. If I want to say this sample, if I give the x1 is the 0.1, x2 is the 0.2, I am expecting y equal to 4.8. So we'll see. I will give the 0.1 and 0.2, and y should be 4.8. Yes, is the y should be 4.8. That's fine. That's how. Now, how we are getting this one? Because your machine learning model, that is the multiple lineage model, already trained. It is already trained. So based on its experience, so if x1 equal to 0.1, x2 equal to 0.2, then it will give the output 4.8. Approximately it is 4.8. That is right. All right. Fine. So this is all about the implementation of the multiple linear regression model from the scratch. That means I'm not using any libraries for the training. See how many lines of code is there here. How many lines of code is there here? From here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 lines. 19 lines in our code we have to to implement the multiple integration model using the Python based on the gradient descent algorithm that what we discussed in the form of the mathematics. Okay. Now, that means now it's the 3 o'clock. Later, that means post break, we will discuss about the implementation of the multiple integration model.